All right, good morning. Hey, I'm just reading up your chats. Thanks for coming by. Good morning. It's April 22nd, Wednesday. It's gorgeous outside, so if you haven't had the chance to go outside, I think it's a great time to sort of go out and enjoy the nice weather, which I think we're due for because it's been a long time. We can wait a couple more minutes because I think, like what Hallie said, maybe the students are just ending their chats. I'm just gonna sort of not like take attendance. I just want to keep track of who is here, so then it just makes it easier for me to know who's here. I'm just gonna type this here. Let me see. Ben is here. Natalia. Oh, I've got Natalia already. Maddie's here. Annie's here. Marina's here. Morgan's here. Nat's here. Cool. A lot of you are here. Janice is here. Good stuff. If I missed anybody, be sure to add your name here or let me know. I don't think I missed anybody right now, did I? But I'm just gonna put this here. Oh, Junior's here too. Cool. I think people are sort of trickling in, and that's great. It's your Wednesday, so I'm not gonna make this that long of a class. Oh, Jaden's here too. I just wanted to go over some of the questions from Monday, and then I do have the answer key for this unit and everything else. Hopefully, you guys all had the chance to finish it. I was thinking of an idea of what we can do, but I don't know if you're game for this. So let me know. Involves some fun, I guess, and technology. I don't know how it would be. It was just an idea that I came up with when I couldn't sleep last night. Trying to make something more pleasant, I guess. So what I was thinking, I don't know if you've seen the video from Calvin. You know how like each student sort of did their thing, and oh, Annie, I forgot. Oh, I got your name. And you know how they did like little clips of them, and then they kind of string it together. So my idea was thinking of maybe we can do sort of like a music video about chemistry, and we can do a little bit of us, and then we'll put all of our videos together into a song or a music video. I think it'll be pretty cool. It might actually catch some attention. It might catch it on fire and kind of thing. But I was thinking of maybe doing like Bohemian Rhapsody, or maybe change the lyrics around to make it like a chemistry themed, about like what your thoughts about learning online, the content. If you think about the lyrics for Bohemian Rhapsody, right? Like it's sort of caters to what we're dealing with a little bit of it, and then we can totally change the lyrics around. I was just thinking about that. I don't know I think if we were to pull this off, like all of us sort of record a little bit of it and then like piece it all together, it would be pretty interesting. I don't know. Let me know about your thoughts. I'm sort of nervously waiting for what you guys are going to write in the text box. I don't know. Radioactive. I don't know if I know that song. Maybe if I listen to it. But I was thinking like first like we'll do like a music video, but obviously we have to change the lyrics to suit like our chemistry class. And I think right now, because we have so much time, and maybe to make something to commemorate sort of this time, right? Because maybe like 3 years later, 5 years later, when you look back, it's like, what did we do in chem class? Well, we just kind of sat down and watched live streams. Yeah, whoopie-doo, right? But if we were to make something, like we do have like 2 months of this, make something, and that's something that will stay for like on for a long time. It also could potentially go viral as well, right? But let me know what you guys think, because I can create a separate channel here, and then make it like for a discussion, like Bohemian Chemistry or something like that, and we can try to string some lyrics together, and then put some of our videos together. I can sort of play the song on the piano, so I was thinking of doing a little bit of that too, and then we'll piece it together. I don't know. Let me know what you guys think about that. We can totally not do this. right, Chloe? That could happen. Like seriously, and I think that would be pretty cool. But I don't know. What do you guys think? And let me know your thoughts. I think it'll be fun to do it, but of course we need like full participation, because then we all have to sort of just like either write the lyrics together and then do a little clips of this, and then put all the videos together. Like you've seen a lot of these YouTube videos of people putting songs together, right? And I think we can do it. And I feel like there's not enough responses in the chat box right now for me to agree on this or to go ahead with this. What do you guys think? Bup, 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 bup. Yeah, no responses. Where's the responses here? What do you guys think about this? Still waiting for you all to respond. Hallie's not opposed to the idea. Lane is down. So, all right. So I guess what we have to do is that we will have, like, I started this channel here, and then we can totally just look into the lyrics. If anyone wants to start writing some lyrics, or just like have like snippets of the idea or lyrics that you want to add in, and then we can have like the instrumental play in the background, and then we can like even write lyrics about what the content is, right? I think we can totally pull this off, right? Hey Greg, I was just having this idea, like what if we did like a music video about chemistry in the song of Bohemian Rhapsody, but like Bohemian Chemistry or something like that. And then that's where we can write our own sort of chemistry lyrics about either chemistry and about like us learning online, or like learning distant, like on live stream classes. I mean, it's not very pleasant, right? And then we can film ourselves like singing snippets of it, and then we'll pool all of our sort of our videos together into one gigantic music video, right? I think that'll be kind of fun. So let me know. I totally just started this channel, and we can start uploading some little bits and pieces. If you guys want to just take the initiative to do some lyrics as well, I have some ideas already. Seriously, I couldn't sleep last night because I was thinking about this, and then I can put some lyrics on and think what I think about it, just to see what the direction of this. We can totally just play it around. If it doesn't work, if it doesn't work, right? If it works, I think it'll be pretty cool. And you know, our school will tweet this out, and maybe it will get a notification by people, right? I think we can all sort of sing a little bit, and then maybe we can have, you know, Lane sing most of it. Well, let's work on the lyrics first, and then we'll play it by ear, and we'll see how it goes. Okay. Yeah. Thanks for doing this. We can sing. We can't. That's totally right. Like it doesn't have to be good. I think it will just be entertaining, and I think it will just be something that you'll remember, something to remember this time, right? Like imagine just having that video that you'll see like 5 years later, and it's like, oh, this is what we did in chem class, and right. And we do have a lot of technology that we can do, right? And do different camera angles. But one thing I want to say is that keep this on the down low, keep this as a secret, right? Because we don't want to be telling, oh, this is what we're doing, because if it doesn't work, or if we doesn't pull this off, it kind of might be a disappointment. So just kind of keep this on a download, and when we release it, then we'll release it, I think, right? Hey, yeah, I think we'll give it a try. I'm gonna try to write some lyrics today, and maybe film just like bits of the piano here and there. And then yeah, let's do that. I'm excited. Okay. If you have any ideas, just keep writing them into your text box, and that's good. If here it is. Here's the first one, and let me just kind of post a video up here then. Bohemian Rhapsody here. If you guys don't know the lyrics, I'm just gonna see if I can share this. I'm sure you guys all know the song, so I'm just gonna. Morgan has a recording studio in her house. That is amazing. We can totally do this. This is going to be great. Chloe, your future employers are going to totally dig it up and appreciate it, because I think they're going to be like, this person is super creative, went out and did something cool, right? That's what people see. I think that's great. Cool stuff. I'm excited. And Morgan can sing. Yeah, I don't know who can sing, so if you're all game for singing, totally do it. And yeah, that's great, right? If you're very savvy with the tech of putting the songs together, that's your role. If you're savvy with like putting video together, man, totally go for it. Yeah, way to go. That is so cool. I'm so excited about this. Now we need some, yeah, and Chloe can choreograph. Right, we need some, yeah, this is great. Way to take the leadership on this one. Someone's at the front door. Who's at our front door here? Anyway, I'm so excited about this. I'm going to give you some of the answers to the average atomic mass worksheet. Hopefully you guys have done or practiced some of the questions. And yes, Donovan's going to do, like, if you dress up for this, right? Like, I'm imagining all of us in, like, just us and then dressed up in costumes or different things. I think that would be pretty cool. Totally. Yeah. All right. Let's. Yeah, I'm so excited. Is my. Oh. Okay, I'm gonna give you guys the answers to this, but you can keep chatting away. I'm just gonna write the answers. But calculating the average atomic mass. Here's the answer for this one: 35.453 AMU. If any of these you want me to show you the work, let me know. Maybe this one I'll show you the work. I'm gonna do 20%. 80% is equal to 17.6. And then 40% of the coursework, and we're going to multiply by 60%, and this is going to be 24. And then 40% times 95% is equal to 38. I'm going to sum all this stuff up. This is your percentage. So this is like calculating your average mark, which is your final grade. That's same as your average atomic mass, right? I'm so excited about this. Like, man, come on. Like, who really cares about average atomic mass when we're going to make a music video, right? For this one, number 3, we have to change the percentages. So 20% will have a mass of 88, and then 40% have a 60. I don't know who came to my door. Somebody delivered something. I'm kind of curious to see who's upstairs. So when we look at this, we're going to use the same percentages and multiply them out. So 0.2, change this percentage into decimal numbers. So this is 0.2 times 88. This is 40%, so this is 0.4. So times this by 60. And then once you multiply all this stuff out, the first one is going to be 17.6. And then this is going to be 24. And the next one is going to be 0.4, which is your 40% here. Multiplied by 95. This will give you 38. You're going to take this number, and this number, sum it all up, and then the total is going to be 79.6 of the mass. Right? So far, so good. Number 4, pretty much the same thing. You're going to take 99% and multiply by 1, and then 0.8% multiplied by 2, and 0.2% multiplied by 3. So make sure that you're moving the decimal places 2 times to the left. So this is going to be 0.99 times 1 is equal to 0.99. This one here is 0.8%. So remember, you're moving the decimal places to the left 2 times. So this is going to be 0.008. So that's your very small number. you're going to multiply this by 2. These numbers up here, 1, 2, and 3, that's your mass. Okay, that's really just the atomic mass of that sort of particular isotope. And so once you multiply this, this is going to give you an answer of 0.016. And then the last one here is going to be 0.2%. So we're going to change this to decimal place. So this is going to be 0.002 times 3. This is going to be 0.006 AMU. So to find your average atomic mass, you're going to take each chunk of the entire piece, and then you're going to add them all up. And if you combine all of them, you're going to get the AMU of 1.012 AMU. Okay, so that's how you calculate that. That's for number 4. Chloe, if you want, let me know if that made any sense. So for the number 5, this one is not, you're not provided with your percentages, but you are provided with the isotope, the mass of each isotope, and the relative abundance. So what the relative abundance is really just the decimal number of your percentage, right? This is just like the abundance, how much it is for this particular isotope. So you don't have to move to decimal places because it's already done for you. It's not in the percentage. So what you're going to do is that you're going to multiply these two numbers together, multiply this number to this number, multiply this number to this number, and then the numbers you'll get, so if you multiply the first two is 18.876, whoop, and then the next one is 2.531, and then the last one is 2.902. You're going to combine all of these ones. It's going to be 24.309 AMU. So if you look at the magnesium atomic mass on your periodic table, you should have the same as that, right? Does that make sense? Did that work out for you? The 5 examples, 5 questions are pretty much repetitive. So they're just kind of the same of how you do it. This one is provided with the percentage. So you do have a percentage and you have the atomic mass. This one should have been superscript, but that's your atomic mass with your percentage, right? So again, change your percentage into your decimal place and then the decimal number and then multiply them out. So for the first one, you should get an answer of 85.56 AMU. That's your first one. And then the next one, number 2, again, it's pretty much the same thing with the percentages, right? This one just has 3, so you have to look at all of them. So all of these ones, once you multiply the number, is 237.978 AMU. Okay, cool. Yeah, I'll go over all of these ones, Isla. Okay, and then number 3, the average atomic mass for iodine. Again, this is all these ones should have been superscript, so it should be 127I because that's your atomic mass. So if you do all of that, multiply them out, this is going to be 126.86 AMU. So AMU, again, is atomic mass unit. And we're going to talk about this a little bit later, what that is. That's your atomic mass. One thing to note for the units for atomic mass is your AMU, but it can also be grams per mole. It's just that we haven't talked about what a mole is, right? You're changing, you don't multiply the percentage by 100. You're actually dividing by 100, right? Because you're changing the percentage into a decimal number, right? So if you score like 98%, the decimal number here is actually just 98 over 100, right? That's your 98%. If you divide by this, you get 0.98. Okay, so that's your how you change that. Okay. How you guys got new clothes?
No, no, this is my dance recital.
They
really?
deliver the dance costumes.
Oh, that's what was at the
You
door.
want to give kisses to Daddy?
Okay, good night.
My little bow.
Okay, good night. That's a really cool bow that you have, Abby. I guess you gotta practice your dance moves.
Kisses for Abby? Yeah, we'll put the video on later.
All right, number 4. So lithium has 2 natural occurring isotopes, lithium-6 and lithium-7. If the average atomic mass of this is 6.941 AMU, which isotope is more abundant. So if you look at this, you have two isotopes. Lithium 6 has atomic mass of 6, right? 6 AMU. The other isotope is lithium 7. So then if you were to sort of look at the percentages, and your final answer between these two is 6.941 as your mass, AMU. So the question here is that would you have a larger chunk of this with the 7 or the 6? Remember, this is this lithium 6 and lithium 7. This is your entire piece of the pie, right? Like 6.94 fills up this entire piece. Are you going to have, for this entire piece, are you going to have more on the lithium 7 side, or are you going to have more on the lithium 6 side? Well, you can see that the number is 6.941, so you're going to have a pretty large chunk of this on the lithium 7, right? Because in order to get this number so close to 7, you're going to have a pretty large chunk. Lithium 6 is a smaller chunk, so this is going to be, yeah, because the number is closer to 6.941. This is a qualitative way of looking at this, because you can just judge from the final answer here is that 6.9 is pretty close to 7, right? So you will have a larger chunk of the lithium 7. So that's really how you can reason that that question out. Number 5, finally, it's the same as the other questions. I think you guys are getting the hang of this. The answer here is 192.2486 AMU. So you probably noticed that for this unit, it's a lot more calculations, and it is a lot more calculations. The theory is more of understanding why we're calculating. So if we're looking at the theory behind this, is more of why are we calculating the average atomic mass, right? Or what's the decimal number from in the average atomic mass or in your atomic mass, right? So now you know that when you look at a periodic table, the atomic mass is a decimal number, and that's because it's looking at the relative abundance, like how much of each isotope we have. And then once we sort of take into account for all of the isotopes, that's your final average atomic mass, right? That's really it. Like I said from last class, we're not going to spend too much time on this because it is, I think, relatively sort of a simpler, I guess, math here, because it's just multiplying and you're just taking and then summarizing or summing the results. What I would suggest for all of you to do is that I hope all of you have done this sheet. If you haven't, write down the answers and then practice it, because you don't want to lose these marks on a quiz or anything like that, because they're pretty straightforward. But moving ahead, I would suggest all of you to, see if you remember how to name compounds again. We have done a lot of this at the beginning of the year, but just to master this, remember, it is really important to know how to name and also balance the charges for naming, right? This is probably like a given in chemistry now, that when you go into grade 12 chemistry, you're just basically assume that you know how to name this, you know how to write the formula for this, or know why this is wrong and why this is correct, etc., etc., right? It's pretty much like you assume that you need to know that, or you know this 100% already. Okay, so give this naming review practice a try. Wonder if we should go over, maybe I'll go over the types of reaction very quickly with you, just so then, because we're not going to see each other till Monday. But if you were to look at the types of reaction, if you have any questions, really just stop me there and just type in your text box and let me know. When we look at the types of reactions, really there's just, do I have average atomic mass? I'll just do this types of reaction here. When you look at the types of reactions, there's actually 5 different types of reactions. I do have a video on this, so if you want to look at the types of reaction, it's right here, 3.8. That's your grade 11 one. Really, you just have 6 reactions, and 4 of them are just pairs. So let me just kind of quickly go over these with you. So number 1 is your synthesis. And then the opposite of synthesis is decomposition. So I'm just going to write these into pairs. And what synthesis reaction is, not decompositions. Synthesis is, if you look at the word, is to synthesize, it's to make things or pair things up together, right? So the generic sort of formula for this one is just, if you have a compound A, compound B, then you're going to pair them up and combine them to get a compound A, B together. That's how it should be. So if you were to look at any of these examples, see if you can find one that is showing two separate things, and when you combine them, you're going to get one thing. So if you look at just really number 2, magnesium and chlorine, if you were to combine magnesium and chlorine gas together, you're going to get magnesium chloride. This is an example of synthesis reaction because you're combining two independent separate ones to get into one big clump. Okay, well, so then if you can combine things, then you can also break apart stuff. That's why the second one, or the opposite of this, is decomposition. It's just the opposite order of this reaction. So instead of having two separate ones like this combining to one big chunk, you have this one big chunk, and it decomposes into two separate independent things. So I'm just gonna double check something right here. Just give me a second here. So if you look at decomposition here, which of these examples can you see that you have one big chunk and then it separates into two separate independent chunks or little chunks, right? The first one. If you look at the first one, this is copper 2 oxide. They're combined as one compound, and as this sort of progresses, it sort of decomposes. It breaks it into two separate pieces. So it started off with copper and oxygen together, and then now it is separated into just copper and oxygen separate from each other. Decomposition, separate from each other. So that's your decomposition. The third and fourth one is your single displacement. So I'm going to say single displacement. And then what this is really just having one switcheroo. So what that means is that if you were to start off with one lonely person, this is like me when I was little, single guy, and then I see my friend and he's dating some girl, right? B and C. And what happens is that, all right, so then, I don't know, I got a new haircut, got super confident, and then I actually ended up taking his girlfriend. This is a terrible example, I just realized. So what happens is that the A switches with B, and they swap places. Now I'm dating the girl, and my friend is by himself. So then B is by itself, plus A and C. That's a single displacement because you have one that is displacing the other. One singular one displacing the other. Not a great example. I'm just waiting for you guys to write in the text box right now. So how does this occur in the chemistry sense is that now we have to look at the charges. So what that means is this, if we were to look at this page, these examples, let's see if we can find one that has one independent one and then one clump one. 6 is an example. It's just not very clear. I want to see if I can look at a very clear one. Number 12 is a very good one. And it's not confession. I'm just trying to make up examples that you guys will remember. I don't think that ever happened. I think people did that to me than me doing to others. So, so let's look at 12 for example. Fluorine gas plus 2 Ki yields I2 plus 2KF. To make this work, let me just kind of fix that this is F because it looks like it was an I sideways. To make this work, it's really important that you know the charges, right? Because you know how I always stress on the charges? You should always write positive first and negative second, right? So the first one, fluorine, doesn't have a charge right now because it's by itself. But when you look at the potassium chloride, you have your positive and negative. And then if you look at the product side on here, iodine is by itself, so it doesn't have a charge. But this one has KF, so potassium is your positive and fluorine's your negative, right? So if you don't remember how to do this, look at your periodic table. Potassium is your metal, so it's going to have a positive charge. Iodine is your non-metal, so it's going to have that negative charge. So what's going to happen is that this fluorine is going to take place of the negative iodine. Why the negative iodine here? Well, because fluorine is a non-metal and it's a negative, right? So this is one of these little details that you have to remember for chemistry. And again, chemistry, it's all about remembering and knowing the charges, because that will help your understanding so much more. So remember, fluorine is a non-metal, so it has a negative charge. It's going to switch places with the iodine. So then what's going to happen is that now iodine is going to get pushed off. So then iodine is by itself. And then now potassium and fluorine are together. You notice that you start off with F2, and then now you have F. Again, you have to balance the charges here, right? So if you remember, potassium is an alkali metal, so it has a +1 charge, and fluorine is a halogen gas, so it has a -1. So then this positive and negative will combine together to equal to 0 to get you a neutral compound. So that's what is KF. So for why, then your question might be, well, why F is 2 and why I is 2 when they're by itself? So here's another sort of detail that you have to remember. These F and I's, I can't pull out my periodic table, but I can show you that anytime you have this, HOFBRINCL. So this is what they call the Hofbrinkel. Hofbrinkel are those elements that when they're by themselves, they have to be H2, O2, F2, Br2, I2, N2, Cl2. So write these down. And the names for these ones are called diatomic molecules. So what that means is that these ones, they have to be a diatomic. That means that they have to have it combined with itself into twos. So they're found into sort of that pairs or twos because they're so reactive that they just can't be found by itself. You're not going to find hydrogen by itself or oxygen by itself. So instead, they will just pair up to each other to make it stable, like oxygen gas, hydrogen gas, iodine gas, or chlorine gas, etc. So Hofbrinkel, those are diatomic molecules. So when they're by themselves, you need to have them have that too. Okay, is that good? All right, so that's your single displacement. The pair up, the opposite, or not opposite of this, but just like a pair to this, is called double displacement. So this is double displacement. This one is a very common one. And what this one is that now you actually have two pairs that's going to displace each other. So what that means is that maybe you have seen this before. I have seen this before. Is basically two couples, AB plus C and D, and they switch partners. And seriously, this is not a confession, but like I have witnessed this before, and I don't think I've ever been in situations like this. But how do they switch places? Again, you have to look at the charges. A negative, or A is positive, B is negative, C is positive, A is negative. So in order for this to actually happen, the charges, the same charges, will swap places, right? Because the positives always have to pair up with the negatives. Positives always have to negatives. Yes, Isla, I feel like I love to experience stuff. So and I like to observe people, and I like to yeah. Anyways, I don't want to tell you too much of my secrets. Anyways. So this A is going to switch with C. So now you're going to have C. I'm going to just kind of switch colors so you can see CB plus, and then now you're going to have A and then D, right? Again, if you look at the charges here, C is your positive, A is your positive, and then your B was negative and negative. Okay, so you have two compounds switching places. That's what you have to do. So if you want to go down this list, oh, totally, that is off the screen. Let me see if I can move this over here. Not that one. Let me see if I can move this one. Can I highlight this stuff and can I just shove it over? There we go. And then, oh, totally, I should move this stuff first. Move my diatomic molecules. I think I'm making this worse here. Oh, I can't. Ah, how do I move this whole thing over? Move like this. Okay, so that's your AB plus CD, blah, blah, blah. If you want to just kind of copy this down so I can move that sheet back over. I don't know how, or just how I can just move that singular sheet. Oh, I'm doing it. There you go. There we go. So if you want to go down this list and see if you can find a double displacement, so let's check it out. Can you find one that you have two double sort of compounds? That means you have a positive, negative, and they're going to switch places. So if I were to go down this list, I can see that 11 is 1. So this is the 11. Double displacement. So I'm just going to say DD, double displacement. And the reason behind this is that if you look for number 11, barium is here. Oh, that's a terrible one. Let me kind of just draw this again. Barium is your positive, chlorine is your negative. And then for H2SO4, this is your polyatomic. So your H is your positive and SO4 is your negative, right? So then what you're going to do is that you're going to have your positive here, negative here, positive here, negative here. And you notice that they're going to switch places, right? So barium is going to switch places with hydrogen. So you notice that now it's barium with sulfate, and then now it's hydrogen with chlorine. So this is where it gets a little bit tricky because now you have to balance the charges. So what I'm going to do is that I'm actually going to show this to you because I think, oh, come on now, work with me here, Microsoft OneNote. I'm going to do this on the side so you can see what that means about balancing charges. So let's start off with just writing this formula, BaCl2 plus H2SO4, and then this is going to yield BaSO4 plus HCl. So far everything's on the screen, everything is good, right? Good stuff. So then the next thing here is that let's look at the charges here. I'm going to find my positive. So if you look at your periodic table, you're going to notice that barium is a +2, chlorine is a -1, hydrogen is a +1. SO4, if you look under polyatomic paper, I hope you have it. If you don't have your polyatomic paper with you, I'll post that PDF onto Teams so then you have access to it, all right? But SO4 sulfate is a -2. So if you look at the other side, this is your +2 and a -2, +1 and -1. So what's going to happen here is that you're going to, let me see if I can use a different color. You're going to switch the positives, right? Because positives and negatives combine to each other. So what you're going to get is that you're going to get barium now is with SO4. So is this formula correct? And if you look at it, barium is a +2, sulfate is a -2. They're going to cancel to equal to 0. That's a neutral compound. So this is correct. Hydrogen is a +1, chlorine is a -1. Again, they're going to cancel to give you 0. Then that formula is correct, right? So that's how you want to look at these ones. And then if you go back to the original one, barium is a +2. Chlorine is a -1 for one of them. That's why you have two of these. I don't know if you remember balancing the charges, but this gives you a -2 in total. So that's why you need 2 chlorines for every 1 barium, because +2, -2 will cancel out. And if you look at H2SO4, the same concept is here. So remember, hydrogen is a +1, but because you have 2 of them, this will give you a +2 in total. And then this +2 is going to cancel with a -2 to equal to 0. That's why it's a H2SO4. Okay, so I know I sort of went a little bit ahead with the balance and the charges, but we have done this before. I just want to review it with you. But this one is your double displacement. So far we've done synthesis, which is combining, decomposition, which is separating. Then single displacement is where you have one of them with two displacing. And then the next one, double displacement, is when you have two of them and then they are displacing each other. Okay, so that's 1, 2, 3, 4 types of chemical reactions. And to be honest, when I learned chemistry when I was in high school, I don't remember learning these types of reactions. And I remember seeing my friend do this, and he's like, writing all these formulas out, our reactions out. I was like, how do you know what they make? And then I realized that these 4 types of reactions are sort of like the templates on how reactions form. And that's really how you predict what kind of reactions you'll have. All right. And I know there's 2 more, so let's go over them. So number 5 is your combustion. So this one is completely irrelevant or not tied into any of the other ones. Combustion is basically burning hydrocarbons. So the standard template for this one is you're going to have a hydrocarbon, which is you have carbons and hydrogens together, and it doesn't matter how many you have. So you can have 2 carbons, 5 carbons, whatever. You can also have 5 hydrogens, 10 hydrogens. It doesn't matter. It's a hydrocarbon, and you're going to combine this with oxygen. And once you burn it, once you set it on fire, then you're going to have CO2 and water. I have a couple videos about this, which I can show you after, but this is the template. You burn a hydrocarbon, so this is your hydrocarbon. And then you need this in the presence of oxygen. And once the reaction gets burnt, you're going to get CO2 and you're going to get water as a result. Always. So that's your combustion reaction. So if we were to look at your sheet here, let's see which one would it be, right? Which one has carbon dioxide and water as a result? Number 5, right? If you look at this one, this is number 5. You have a hydrocarbon, carbon, hydrogen, right? And then combine it with oxygen. This, if you burn it, you can get CO2 and water. So this one is your combustion. I'm writing this with a mouse now. Combustion. Okay, so that's your combustion reaction. And then the last one, if you have any questions, if you think I'm going too fast, just let me know. And it's super messy on my screen right now. I wish I can just erase this. I don't really know how to do a massive erase. Okay, so number 1, 2, 3, 4, 5 is super messy. And then the last one here is, let me start off here at the bottom. This is your acid or the neutralization. And we'll come back to this a little bit later, but this is just, you have an acid plus a base, and then this is going to give you a salt and water. That's really the neutralization reaction. I'll just have you sort of write this down first. I don't want to go into too much detail today. I feel like I have given you a lot of information just on one lesson. So just write this down, and then we'll go over this neutralization next week. But these are your 6 types of reaction. And if you need a little bit more pointers, again, I do have tutorial videos on this, which actually is a little bit better than how I described it, because I have examples of what each of these reactions are. So you can see that I was a lot younger back then. It was 2015, but let me see. Okay, wrong video. But let me show you an example of a combustion here. This is a combustion reaction, and
So would you like to see it? Of course.
I'm gonna just skip to this. What I did was that I put alcohol in this jug, and because alcohol, like if you remember, has a very high vapor pressure, so it evaporates and vaporizes really readily. So then that liquid alcohol changes into vapor, and then it gets trapped into this jug. I sealed it, and then
light this on fire, but be careful that the lights can do a short.
so then once I give it some time, the vapor vaporizes and gets trapped into the jug, and then I'm gonna lit it on fire. So check it out.
5, 4, 3, 2, 1. Oh, look at that! Whoa, look at that. The fire's still burning the excess alcohol. You have to wait till it cools down. Make sure everything is safe before you touch this because this is gonna be hot.
Even at this stage, okay, you might not see any flames inside the container, okay, especially the neck. You don't want to pour it out or just flip it over or invert it because you never know, okay?
Just let it settle.
Just let it settle.
Whoa, I have this
Yeah, so that's an example of a combustion. So at the end of this, I didn't really show you, but inside this water cooler actually has water there, which is really neat because you think that you're burning something, you will burn off everything. But as a result of a combustion, you actually have a water as a residue or a leftover product, which is really, really cool. So that is a combustion reaction. Let me kind of go back to the work booklet, and I think Isla, you had a question that which one is an example of a neutralization. I don't want to go over the neutralization to show you an example just yet because then in order to answer that, then I have to teach you how to identify an acid or base. So what I would say is go over this page and identify the 5 first. If there's one that you're sort of iffy, just leave it, but we'll come back to this on Monday. Or if you have any questions, just send it to me through email. I can answer it those months. It's just that identifying acid and base is sort of another lesson in itself, so I don't want to sort of bombard you with so much information on today. All right. Number 7 would be a combustion reaction, and that would be a combustion reaction. And if I were to look really quickly, I feel like now I'm just kind of, not listening to my own advice here. I don't see any neutralization reaction in this page, so there goes what I was gonna say. But yeah, don't worry about neutralization in here because I don't think it's there at all. All right, I think that's good for today because I think that was already like 50 minutes. Thanks for coming by. If you haven't told me if you're in the chat, can you just quickly tell me that, hey, I'm here, whoever is here, so that I can just kind of keep track on Teams of who attended today's live stream, because it just helps me kind of keep track. So if you can just quickly type in your name or just your initials so that I know, that would be great. And I know Greg was here too, so I'm just gonna put that on there. But that's it. Thanks for coming by. I have created that channel. Maybe if any of you want to start writing some lyrics down, or if you have any ideas what this music video is going to look like, go onto the channel, onto Teams, the Bohemian Chemistry one. Let's share some lyrics, share some ideas. I think it's great. All right, so I'll see you all later. If you haven't, let me know who's here. Yeah, just type in on chat on Teams. On the yeah, Guy, I got you. I got Guy and June and Ethan. Marina's here. Oh, I got Marina already. Also, but like, if you have any ideas, put it onto Teams. Great to see all of you all here. That's all today. So have a great day. Go outside. It's gorgeous outside. See y'all. Bye.